And we're now going to move on to Module 4, where we'll continue to talk a little bit about climate change and how it affects ecosystems and ecosystem health and public health. I'm going to remind you that as we talked at the last section in Section 3 about temperature effects, and now we have a slide up here that sort of zooming down from the global impact of temperature change. Let's zoom down to the southeast U.S. and talk a little bit about how temperatures are changing in the southeast U.S. Temperatures have increased by 2 degrees Fahrenheit since the mid-1970s, and most noteworthy are the number of days at or below freezing have been decreased by 4 to 7 days since the mid-1970s. Our winters are much milder, and you can clearly see here in South Carolina the effects of that in terms of much milder winters. That's not to say that we still can have extreme weather, but on average, we are seeing 4 to 7 less days of below freezing temperatures. So when we begin to look at the effects of climate change, one of the things that we really see is what we like to see more extreme. We see more extreme temperatures, both cold and warm. We see effects such as heat waves. We see increased precipitation events for heavy precipitation. We have extended periods of drought. Both ranges in terms of precipitation, no rain, heavy rain. We see increased activity for tropical cyclone activity. We see increased sea level rise. So overall, we see increased extreme weather. That's what this little graphic is placed here on the table right out of the IPCC report, just to make that point. The other thing we should mention too, when we talked about urbanization in our preceding modules, we also talked about increasing runoff. And what urbanization does is it also makes the runoff of precipitation and weather extreme. So what we are doing with the combination of climate change and urbanization is we're kind of producing this double whammy effect of making things more extreme. Now, this is a slide, the preceding slides have been air temperatures. These are actually changes in global sea surface temperature from 1970 to 2004. So wherever you see temperatures that are brown or green, where we see like in the southeast U.S., we do not see much change in temperatures of the seawater. But take a look, if you would, at Alaska. Notice how it's at the extreme end of climate change. And the areas that are in the higher latitudes are pink and reds. That's because the effect of climate change is much more extreme in the higher latitudes than the mid or lower latitudes. And that's what this slide depicts. So we said there will be increased melting of polar ice. And we talked about the fact that ice in the Arctic has accumulated much in the way of air pollution from the Industrial Revolution for the past couple of hundred years. According to the Arctic Climate Impact Assessment, the Arctic temperatures have increased anywhere from 7 to 13 degrees Fahrenheit, and that's 4 to 7 degrees C during the same time frame that we are looking at in terms of this century. And so it's expected by the end of the century that we will have full melting of a lot of the ice in the Arctic. So nowhere else in the world are we seeing temperatures forecast to increase as dramatically as in the polar regions. The average temperatures, the second bullet from the bottom kind of captures this. The average temperatures have increased almost 0.5 degrees centigrade globally, and that's enough to really shift these major weather patterns. But the change in the Arctic and Antarctic regions is much more profound. And of course, this puts many of the creatures in the Arctic at risk. Your polar bears that rely on hopping from ice floe to ice floe in their hunting. We also see Adélie penguins and walrus as some of the prey that polar bears utilize, all of which will be adversely affected by the lack of the polar ice cap in these regions and that habitat shrinking. So think of it just like urbanization. With urbanization, we pay paradise, put up a parking lot, and we take away the green spaces. Where do all the wildlife go? Well, the same thing is true in the Arctic in terms of global climate change. As the ice flows disappear, where do all these animals go? And will they still be here 100 years from now? And at what levels? Will we only see them in a zoo? Now, I mentioned the capture of industrial pollution from the Industrial Revolution in the Arctic ice. As that ice begins to melt in 40 to 50 years, these are the levels of different levels of trace metals that we see in the ice that will be discharging into these polar regions. These are in parts per trillion, so you can see 100 to 200 parts per trillion lead, 1 to 8 parts per trillion mercury, and 3 to 38 parts per trillion cadmium. Now, the first thing you're going to say, Geoff, those are not very high levels. But let's come back and we'll talk a little bit more about that in just a moment. The next slide lists some of the pesticides that are sequestered in polar ice. One pesticide that's most commonly found in the Arctic, the most commonly found pesticide, is a pesticide called indosulfan. It's actually used on tomatoes to kill stink bugs. But it ends up, because of its Henry Law constant, which means it's evaporated into the air, and most of it ends up in the atmosphere, it's the #1 pollutant we find in polar bears. So even though we don't raise tomatoes in the Arctic, polar bears have this as their major contaminant in their lipids. So you'll notice there's anywhere from 30 to 360 parts per trillion of indosulfan. What's critical here, the water quality criteria is only 8 parts per trillion. So these levels in the Arctic will be way above water quality criteria. Second pesticide is chlorpyrifos. If you own a home built in South Carolina or the U.S. from 1989 to 2010, you have to have a legal document that says there's 25 pounds of chlorpyrifos under your house. It's called a termite letter. And that's how much of that pesticide is used to treat your house and structure to prevent termites. The water quality criteria for that pesticide is 6 parts per trillion. Again, you'll notice the levels in the Arctic in the water melting will be 2 to 3 times above that water quality criteria. We also have a pesticide, a herbicide called atrazine, and also DDT, which will all run off into these systems. In fact, if we look at the bottom of the table, there's a little note about the Antarctic ice sheet that's melting. We see anywhere from 1 to 4 kilograms of DDT is entering that one small bay in Antarctica because of the melting of the ice. Now, one of the most sensitive species to these pesticides will be invertebrates, your krill. You may have read recently how krill are dying out in the Arctic. Most people are attributing that to a loss of ice habitat, and that may very well be true. But these pesticides add additional exposures, which may also cause toxicity and effects on the krill. And of course, the krill are vital to these food webs in these boreal ecosystems where a lot of your fisheries production worldwide comes from. Now, this next slide talks a little bit about the impacts of increased thermal stress. This slide is a table taken from a paper published in the Journal of Environmental Toxicology and Chemistry by Petra et al. What it depicts is 4 species of freshwater fish exposed to very low levels of indosulfan and chlorpyrifos, the very 2 pesticides we said were found in melting global ice. And on the far right, you'll see their average thermal tolerance, their upper thermal tolerance. For example, let's use the rainbow trout. The upper thermal tolerance is 25 to 30 degrees C. But you'll notice that if we expose these fish to low levels of these 2 pesticides, we reduce their upper thermal tolerance to as low as 19 degrees centigrade. So at the very time the climate temperatures are being dialed up, we're turning the thermostat down in these fish species, and you'll notice for almost all 4 species, we see that same trend for these two pesticides. What that may mean is mass extinction of these freshwater species because of the intersection of climate change and the release of these toxic chemicals into the environment from the ice. Another effect from climate change is the ecological shifts of different organisms, both marine organisms as well as terrestrial organisms and insect vectors. This next slide is a slide from Dr. Tom Peterson looking at what we call plant hardiness zones at different times. And so you'll notice if we start to the far left in 1990, we only see that light green coloring. You'll now see the yellowing to indicate a new plant hardiness zone showing up on the southern end of Missouri. And now we see as we move ahead in time that the light green community moves farther north, creeps farther north, and the yellow community moves even farther north. This is the area we were talking about, that shifting of the breadbasket, and that's because these optimum temperatures for growth of both agricultural crops and plants will be shifting farther north. Another species that may be affected by increased temperature are mosquitoes. We know mosquitoes vector malaria, dengue fever, and so both increased temperature and changes in precipitation will have dramatic changes in range extension and the periodicity with which these insects are problems each year. Rainfall will increased rainfall will expand the areas, while decreased rainfall will make the complexity of the mosquito breeding areas different. And then sea level rise also will play in terms of increasing salt marsh mosquito populations. Remind you, South Carolina was the last state to eradicate malaria in 1952. So even though we have eradicated it, we still have to be worried about other diseases besides malaria, encephalitis, and other vector-borne diseases. One mosquito-borne illness is dengue fever, and this current slide in yellow shows you the distribution of dengue fever from 1976 to 1995. You'll notice, look particularly at the United States, we mainly have problems right on the border in the southwest with Texas and Arizona and New Mexico. Here's a predicted forecast model using percent changes in humidity to using vapor pressure as a surrogate for humidity. And what I will point out to you is look in 1990 and then 2085. You'll now begin to see that this particular illness is spreading at farther, higher northern latitudes throughout the southeast United States and other parts of the world. So this is an example of where we will expect to see expanded vector-borne disease problems from mosquito-driven illness or mosquito-vectored illnesses. Another example with climate change of a changing paradigm in terms of distributions of illness are with Vibrio bacteria. We're all familiar with Vibrio cholera and how Sir John Snow was able to track cholera to poor sanitation in Great Britain back 300 or 400 years ago and really sort of became the godfather, if you would, of epidemiology. Well, the cholera illnesses today, we still have cholera, and I'll show you that. But we have other illnesses such as Vibrio parahemolyticus and Vibrio vulnificus. And in fact, we have seen a tremendous range extension of some of these species. For example, in 2004, there was a 1,000 kilometer northern range extension of Vibrio parahemolyticus all the way to Prince William Sound in southern Alaska and the Gulf of Alaska. What normally is an illness in the Gulf of Mexico has now become an illness in southern Alaska. Basically, if we look at this is probably with the Vibrio parahemolyticus, this is one of the most significant examples of climate change. What we really see with this outbreak in Alaska was for the very first time, water temperatures averaged above 15 degrees C. And in fact, we saw about a 0.2 degrees centigrade increase each year during July and August when these illnesses occurred. So we began to see now that this illness is now moving to higher latitudes. We have similar reports coming from Baker Austin in Europe, where we see reports in the North Sea and other high latitude areas around the world. Now, Rita Caldwell, who's professor emeritus at the University of Maryland, has showed very clear correlations with cholera illnesses with sea surface temperature, precipitation, and chlorophyll, that is, nutrient enrichment in the Bay of Bengal, so that we can actually develop forecast models to predict Vibrio illness. Now, these are some slides just to illustrate to you examples of illness with Vibrio parahemolyticus and Vibrio vulnificus. Those bulbous lesions you see on the hand and leg, those are Vibrio vulnificus infections, which account for over 80 to 90% of all seafood-related illnesses in the U.S. The fatality rate with this particular illness is over 55%. So it is a very virulent organism, which leads to a very poor quality of life and a very painful death, as the only way you can deal with those types of infections is to amputate the hand or the leg as you try to save someone's life. We mentioned the Vibrio parahemolyticus being expanded up to Alaska, and one of the things that Rita Caldwell says globally, in the last 10 years there has been a 41% increase in the number of Vibrio infections worldwide, and the number of antibiotic-resistant Vibrio infections in that same time period has increased by 31%. So what we see is not only an increase in the number of Vibrio illnesses, but the virulence of the organism is much different. This next slide is a slide by Kay Hoag at the Centers for Disease Control. And what they have basically found from 1996 to 2003, Vibrio infections in the U.S. increased by 80%. Did you hear about that? There hasn't been a lot of notoriety about this, and what we have seen, and what's most important about this, is we actually had a decline in the number of cases of illness from seafood, which were the driving forces that caused many of these illnesses, to more wound infections from people swimming. So this represents a dramatic change in the virulence and etiology of these diseases.
Go.
These are more updated statistics from the CDC, and basically comparing 2012 with 2006, 2008. And what we see is in that 6 to 8 year, 4 to 6 year period rather, is a 43% increase in Vibrio infections, continuing this ongoing increase of Vibrio infections in the U.S. And so I think what this really illustrates is the effect of climate change on this Vibrio illness as a factor. So as John Snow tried to figure out what caused Vibrio cholera cases, today we're really focusing on a new detective story, that is trying to understand how these Vibrio illnesses are increasing, what are the driving factors, and we'll explore some of that in the next module.